Good morning, everyone, and welcome to our ninth conference of the 22nd edition of our RXN, Congress of Chemical Engineering. Today, we have the honor to be with Dr. Paul Alers, Head of Product Management at Bosch Manufacturing in Switzerland. He's one of the Bosch leading vacuum experts and supports various vacuum innovation projects. Recent achievements include supporting Hyperloop projects as well as the ITER fusion project in France. Dr. Paul Alers joined Bush in 2005 and has been acting in several senior product management and application support functions. Dr. Alers holds a master's degree in chemistry from the Technical University of Eindhoven, Netherlands, and a PhD in microtechnology from the University of Neuchâtel, Switzerland. Remember, you can make your questions through the link in the comment section or directly through chat. Please give a warm welcome to Dr. Alers.
Okay. There we go. Well, welcome everybody. Thank you all for having me here on this great opportunity to tell you something about the world of vacuum. So this is a talk which is actually about nothing, because vacuum is empty space, and the more empty it gets, well, actually also the more expensive it will get. But we will see that in a minute. First, something about myself. Head of product management in title, but I'm also heavily involved in many big projects as a vacuum expert. I'm based in Switzerland at the moment at our manufacturing site of Bush in Switzerland. Just a small thing about Bush, we're a family company, so owned by the family you see here on the picture, the Bush family. This is where the name Bush comes from. And we were founded in 1963. We're one of the world leading vacuum companies worldwide. A couple of small facts about our company. About $1 billion turnover of all the companies involved in the Bush Group. We actually have 44 countries where we're active. So that means where we have our own sales companies, service support, engineering facilities, everything you need for vacuum support. 6 manufacturing sites at the moment and about 3,500 people working for us. And most importantly, in 2006, we have actually established also our offices in Mexico. So you now have fully local support in Mexico as well. This talk will be about vacuum, and vacuum is actually used really everywhere. There is actually probably in your room nothing you can point on where not at some stage vacuum was used to produce it. Might it be something like a simple water bottle, your computer, your table where you're sitting, all of those, somewhere in the production, they will have had some vacuum involved. So what I would like to do with you today is to discover a bit what is vacuum, how does vacuum work. We will take this from some historic background of vacuum. So who did actually think first about vacuum? What is vacuum? Some simple feeling of what vacuum can do for you and why we use vacuum. And most importantly, we will have time to look at a couple of examples involving vacuum. The definition of vacuum, where does vacuum comes from? Well, it comes from a Latin word, vacuum, and it means empty space. And now most people will say, well, empty space, well, I could have thought of that. But what few people realize, once something gets empty, it cannot be more than empty. This is where many times things go wrong when people think about vacuum. It's easy to say if you need, for instance, compressed air, that you would like to have 5 bar, 10 bar, 50 bar compressed air to use for your technical equipment. Vacuum, as soon as you go from atmospheric pressure to 0 bar, you cannot go to below 0, because as soon as all the molecules are removed from a room, well, you cannot have antimatter, at least not for the moment. So there is a limit to vacuum. So why do we use vacuum? Well, there's a couple of things vacuum can do for you. One of the important things is, as soon as you have a pressure which is lower than your surrounding pressure, then the room where this pressure is lower will actually have a force on the surrounding. And the most simple example is actually a vacuum cleaner. You will create under pressure in the vacuum cleaner, and that will create a suction effect which allows you to remove the dirt from the floor. Very similar things are used also for holding and lifting equipment. So you could use, instead of sucking the dirt from the floor, you could put a suction cup on your vacuum cleaner, and then it will stick to a surface where you put that suction cup, and you could lift it. So it's used for tactical lifting equipment as well. Filtering. You can imagine you make your coffee, you pour water on your filter, and it starts to drip. If you would, under the filter, now apply under pressure, so suck vacuum, yeah, of course, your coffee will be pulled in much quicker. So in industry applications, this will be one of the uses. The force of vacuum. What you see here is actually an example where you have a plastic foil, and beneath the plastic foil, there is a metal shape. And what this machine does is actually, out of a simple plastic foil, it will make plastic cups, which you then can fill, for instance, with food or other products to seal them later and package them. So how does this work? So as you can see, by pulling under pressure in the shape, the vacuum will pull the plastic foil into this shape, and now you have formed, this is the forming process, by the force of vacuum. So very common in many industries to use vacuum to make shapes in plastic, for instance. Another reason for using vacuum can be that you want to remove molecules in a room. So for instance, if you would like to melt metal, it will get very hot. And if metal gets very hot, well, it will get in contact with the air in the room, the oxygen, and it could start to oxidize, so rust. In order to avoid that, if you want to heat the metal very high in temperature, well, what you do, you put it in the chamber and suck the air away so there is no oxygen remaining. This is also done, for instance, in packaging of food. Because food, if it's in contact with the air, the oxygen in the air will make the food go off, spoil the food, and you can no longer use it. So if you want to have it for a longer period of time, well, you put the food in a plastic container, then you use vacuum in this chamber to remove the air. However, now, if you don't do anything more and seal the package, what will happen is the force of vacuum will crunch the packet because there is nothing left in that package. And if you look in the supermarket, all these nice plastic food packages, well, they're not all scrambled together. So what people do in this kind of packaging method, they remove the air and then they fill it with another gas mixture with a lot more nitrogen and most of the time no oxygen. But if it's red meat, they will put a lot of oxygen. A lot of oxygen makes the meat look very nice red. Like us, if we breathe well, we look nice red. And a lot of oxygen actually is toxic for many bacteria. So more oxygen than in air can actually be very good to preserve the food as well. So actually, the packaging of food is already quite a technical procedure to keep the food well for a long time. One other reason why you might remove the air is that as long as there is air, the heat can be conducted by the air. So you can remove the heat by the heat going through the air. So if you would have a thermos bottle, the one you use to keep your coffee warm, it's a vacuum application. It's actually a bottle in a bottle. And between the two bottles, the air is removed. So now, because there is no air, the heat which is in the liquid in this bottle can no longer disappear through the wall to the outside because there is a very well isolating layer, which is vacuum. Vacuum is actually the best thermal isolator there is. So your vacuum coffee bottle it's already again a vacuum application. There are many other industry processes which also depend on the removal of air. A more technical side, if you want to move, and you want to move in a room, and the room is filled with a lot of people, it will be difficult to move from one side to the other side. Well, that is the same thing for air and other molecules of gas in a room. When the room is at atmospheric pressure, there are many atoms, so it will be difficult to move. So if you would like, for instance, to do a thin film layer on a surface, you're evaporating metal and it needs to move to the surface where you want to have it. If in between it's very densely packed with gas atoms, well, every metal which will evaporate will hit a gas atom first. So it cannot freely move far enough to reach the surface where you want them. This is what we call the mean free path. And the more air you remove, the less atoms in the room, the further you can move before you hit something. So this is also one of the reasons to use vacuum in many applications. Finally, what they call technically the low monolayer formation time, it means no surface is clean. Any surface you have around you, there will be a layer of absorbed water. The vapor of water in the air will cover all the surface of, for instance, your table or what other object you have in front of you. Now, for some technical processes, you don't want dirty surfaces. So to clean a surface and keep it clean, you need to go to very deep pressures, because otherwise there are sufficient gas molecules still in the room that as soon as you remove the surface dirt, they will immediately absorb again. So that is another reason you use vacuum. Keep surfaces clean. Now let's think a bit who actually thought about all of that. The first documented proof of a vacuum that people thought about under pressure and what actually you can achieve with that, that was Mr. Galileo in Italy. And Mr. Galileo, most people know him because he had many problems with the Roman Catholic Church with his theory about the Earth being round and turning around the sun. At that time, the official theory of the church was still that the Earth is flat and the center of the universe. So he got a lot of problems because of that, but he got also a lot of problems because he said, look, if I take a tube and I fill it with water and I close it on one side, and this closed filled water tube, I pull it up more than 10 meters, 11 meters actually, then the top of the tube all of a sudden will become empty space. We know now that is true because of the weight of the water, you will generate vacuum in the top area of that tube. So Mr. Galileo discovered that, and the Roman Catholic Church was very upset because God is everywhere. So empty space cannot exist. And then Mr. Berti, another Italian guy, he was mandated by the church to prove that Mr. Galileo was wrong. And he did this experiment like you see on this drawing, and he proved Mr. Galileo is right. Berti, this is linked to the bar unit. So many of these people who invented some measurement methods, this is what the vacuum units are called now. Mr. Pascal made a theory about what is it? It's a force on a surface area, theoretically. Mr. Torricelli said, well, if you need 11 meters of tube, that is not very easy to measure things. I'll replace the water by mercury, liquid metal, high density. And he achieved the same measurement as Mr. Berti did, but he only needed 760 millimeters to do it. The Thor unit was born. And this is why 760 Thor, 760 millimeters of mercury, is actually the same thing as 10 meters of water or the bar unit, verti, the measurement method. What I'm showing you here is done by a certain Mr. Edmond Carré. For the people who are more technical, they might have heard about the Carré cooling cycle. That was done by his brother, Ferdinand Carré. And it's actually the foundation still of any modern cooling process, including the fridge in your home. But what he actually did, he did the first part of the discovery. And his first part of the discovery is an ice-making machine. At the time when Mr. Carré invented this, having ice in the middle of Paris, he was in Paris, well, it was not obvious because ice was only in winter or in summer if you went very high up in the mountains. So making ice on site, that was really an achievement. Now, what he did do, he made a vacuum pump. So you see here a buffer volume, a piston to generate vacuum, and he attached a sealed bottle with water. Now, if you lower the pressure, so if you would have a cup of water in vacuum like you see on this picture, and you would lower that pressure, what will happen is actually water starts to boil at room temperature. The physics of liquids, if you lower the pressure, the boiling point of a liquid will go down. So he achieved boiling water. So the water will boil and evaporate. If water evaporates, you need heat. Look at home. If you want to boil water, you need to heat it quite a lot before it starts to evaporate. Well, it happens also on the vacuum. But I just told you vacuum is very good in thermal isolation, which means where does the heat come from to boil and evaporate the water? Well, it will come from the remaining water. And this video will show you what happens then. The pressure will go down. You see, the water starts gently to boil. We're in this glass, and you see the temperature of the water starts to drop while it's boiling because heat is extracted and no heat can come from the room. And you see at the end of all of this, the water will quiet down because actually it's freezing. And this is what Mr. Carré demonstrated. 1850, this is around the world exhibit where the Eiffel Tower was also presented. A big technical innovation for that time. One more of those innovations, of course, Mr. Edison, he used vacuum to be able to make an electric light bulb. If you just use electricity to have a filament of metal, a metal wire being heated and emit light, that wire will burn very quickly. So what Mr. Edison did, he actually removed the air around that particular metal wire with a glass bulb around it. And he emptied it completely, so there is no more oxygen there, so you can no longer burn the wire. The second thing, which is very good, there is no more air, so all the heat will remain on this electrical wire, which makes the brightness a lot higher. Okay, from a bit of historical introduction, let's see what vacuum does in our day-to-day life, and a bit later, not so day-to-day life. Food. Everybody needs to eat. So what does vacuum have to do with food? Well, let's look first at something, one of the things Mexico is very good at. Mexico is the biggest worldwide avocado exporter. And they will export avocados. And if it goes to the US, it usually will be pre-prepared half avocados. And it will be also in the form of guacamole, because this is what you will always see if you go to a restaurant in the USA. They will have some of these nacho chips with guacamole served for you. And it's big business. We're actually talking about 2.8, 2.9 billion US dollars per year. And actually, USA is the major market. About 2/3 of all exportation goes to the USA. How do I know that? thanks to Bush Mexico, because actually this particular industry branch, I can tell, uses a lot of vacuum. One of the reasons is the following. These avocados, they need to stay fresh. The half avocados, which the Americans love because they are too lazy to peel it themselves. Well, we make it convenient for them, but it needs to be fresh and keep fresh. So there should not be any oxygen because otherwise they turn brown very, very quickly. So what do people do? They use a plastic bag. The plastic bag goes in a vacuum packaging machine. So you will have a plastic bag, the avocado, which is in there, some chamber, some pump to generate the vacuum, and some valves for the technical operation of the equipment. Now, how does that work? Well, one thing I need to learn to you first. Vacuum is a force. So which means it's a force on a surface area. If you have now an area which is empty, you took away the air, then the outside air will press this area together. And that is what you're going to use in a vacuum packaging machine. You're going to empty all the areas around the plastic bag. So it will be empty on top of the bag, inside of the bag, in front at the open side of the bag. It will all be vacuum. What you do then, you seal the entrance of the bag. So the bag is in vacuum. The outside is also in vacuum. And what you do then is you put air in the outside. And because inside is vacuum, outside is pressure again, the plastic foil will completely stick to the avocado and it will be fully packed. Even in the guacamole manufacturing, so now you're going to say, well, guacamole, that's not half shelf, so why do we use the vacuum packaging? Well, we still use it because when it's ready, it needs to keep fresh. So it's also put in vacuum bags to keep it fresh. But in the manufacturing, if you mix the guacamole with the spices, there will be oxygen inside of that mixture. And if you leave it there, it will also start to attack the quality of the product. So it goes to some highly technical equipment, which is also by vacuum pumps kept at low pressure. And the guacamole mixture, all the air bubbles will be removed using the vacuum. And now you can pack it and it will stay fresh a very long time. Did you ever think that your bread you buy in the supermarket involves vacuum? Well, people can imagine that if I make bread, you take some dough, you bake it in the oven, and you have a bread. Well, traditionally in industry, it's the same thing, although they do very many breads in a continuous oven, and you will get a street of hot breads coming out of that oven, and then it goes in these big towers because you cannot package and put it in a plastic bag until this bread is cooled down. So it takes a lot of time and it takes a lot of space as well. We're getting technical again. We're going to use physics and vacuum to help to modernize the bread and the cooling down of the bread and the packaging time and the space you need for the bread. First, you need to know that if you have materials, they can be solid, ice, they can be liquid, liquid water, or they can be gas if you evaporate water. And if you go from one state, so solid to liquid, you need to add heat. So in this direction, you need to add heat. If you would have liquid water and you want to make it solid, you need to extract heat so the temperature drops. So you can play with the heat. Finally, what kind of condition a material is in depends on what temperature you have, what kind of pressure you have. So water, for instance, if we are at ambient pressure, water atmosphere, about this level, and we would be at 20 degrees, we would be in this area of what we call a phase diagram. The phase diagram will explain what kind of state the material is in. So we would be liquid, and if we start to heat at atmospheric, sometimes here it will be 100 degrees, water starts to boil. And if you would go the other way, then here at 0 degrees, water starts to freeze and it becomes ice. And we already saw on the example that if you are here, so you are water, but you start to go down in pressure, then somewhere you will reach this point and water starts to boil. The video we just saw before. Again, if you go from this side to this side, you will need to add heat. And if you want to go the other direction, you will need to remove heat. And this is the trick we're going to use. Once the bread is baked, it's no longer going into the cooling tower. It goes in a much more compact way in this chamber, which is actually a vacuum chamber. So the operator will put it in there, the door will close, and we will remove the air. What will happen? You will be in position 1. You know, the water is at atmospheric pressure and something like close to 90 degrees because it just came out of the oven. And this is about the remaining water which is inside of the bread. The bread is not completely dry. There is still some water in it, otherwise you couldn't eat it. So what will happen is as soon as they lower the pressure, you will go to point 2, which will mean some of the remaining water in the bread will evaporate, will start to boil and evaporate due to the vacuum, like we saw in the video. So what will happen? It will remove some of the water, which will finish the baking process. There was still a bit too much water. And at the same time, if you start to evaporate water, it needs heat to actually evaporate. So you will remove the heat from the bread. So the bread within a few minutes will be cold, and also the excess of remaining water is removed, so the baking process is finished. Big savings. It means that you only need 90% of the baking time because you want some extra water in there. The hot bread will cool down in a few minutes. So instead of turning in the big towers for an hour or 2, you only need a few minutes. And of course, this takes not much space. Now, in many of the modern bakeries, industrial bakeries, this is the way how they actually cool down and finish the baking of the bread. Look a bit into the health. You know, health is also very important to everybody. So what does vacuum do for you in health? This is what everybody must know. Vaccine. Fortunately, now we have the vaccine and we're going into the phase where a lot of people get vaccinated and we can live freely again because we don't have to worry about the COVID anymore. Well, as you might know, these vaccines, they are stored under conditions in small bottles, frozen. They're very temperature sensitive. So the active vaccine is very sensitive to temperature. So we need to keep it cold. Otherwise, we cannot keep it a long time before it's no longer active. It means that what they do, they actually have the vaccine, the small bottle here, which is some kind of powdery, half liquid kind of mixture. And this is kept in a very cold place. And what they do, they actually get 2 bottles in the vaccination center. One is with the vaccine, which is stored very cold, and one is with some salt solution, which when they want to use it, they will add it to this bottle of vaccine, concentrated vaccine, and then they can inject it to many people. So actually, the vaccine is not the pure vaccine as it was before. It is actually already a concentrated form of vaccine. Now let us see how we take care of that part of it. If we produce the vaccine, it will be done in very big tanks. They will make the active components, but what you will have is a lot of liquid with a few active components. and you need to concentrate it. So what you could do, you could filter it. It doesn't work in this case because it's fully dissolved in the liquid of the production. Or you could try to heat it to evaporate it. So go from point 1 to point 2, liquid to gas, and then concentrate the active component you actually want to transport. With this vaccine, it's not possible. Any heat will destroy it. So cooking it to get rid of the excess liquid is not possible. So what people do technically is what they call lyophilization, or also freeze drying. They make use again of vacuum. They will take point 1 and then freeze it even more so that the whole liquid becomes a block of ice. And then they will lower the pressure until they reach point 4. And now all of a sudden, the ice will go into water vapor and can be removed easily, leaving only the active vaccine component in the bottle. So technically what you will have the bottle with the excess mixture, with the liquid on top of that. Then you will freeze it. It will go down to a very deep pressure, and some of that water will be removed by what we call sublimation. And as soon as all that excess liquid is removed, so the vaccine is ready. As you can see, there is already a cork, but the cork is in an open position. So what they will do in the vacuum chamber, they will push here in this chamber everything together so it closes the bottle. And as soon as the bottle is closed, they put air around it. And now all of a sudden, because here is still vacuum, this cork will be very well sealing the bottle as well. And then you can do what you see here. Have one bottle with the concentrated vaccine kept in a cold place. And once it gets to the vaccine center, you prepare it for the patient. Lyophilization, it uses vacuum. Let's take another big problem for health. You must have heard that, unfortunately, due to our poor diet, many people somewhere in their life have a risk of getting diabetes. Now, diabetes has also the risk that people will get wounds which have very big problems to heal. Diabetes, if it's severe, people, when they have a wound, the wound will not heal properly, and it could go on forever and ever. And actually, this problem with diabetes, about 415 people have diabetes worldwide. Well, 25% of them can develop such a chronic wound. So that's a lot of people. And in the worst case, it will get some really bad infection, and they need to amputate people. So it can be a very bad consequence. And it has a big cost, $13 billion in the USA only. So people thought about smart things to take care of it. And key to this is how you treat the wound and how you make sure that the bandage is still okay, and how that bandage could become even an active biostimulator to help healing the wound. And what people did to do that, they made smart bandages which is not just a covering material, but an active sensor and stimulating material. And they use very special carbon materials, which are called graphene for that. Now that graphene, you see here the atomic structure, so it's a highly structurized carbon material that can be produced in high vacuum special equipment, where with carbon vapors, methane or that kind of gas, with a lot of energy and the appropriate pressure conditions, they can deposit on the vacuum, grow this kind of material. That material then will be put into a bandage, and actually what you have, this bandage will have here fine lines of this graphene material in contact with the wound, with some coil which allows it to connect to a smartphone, to an application. And this smartphone then can read specific conditions of the wound, if it's healing well, or if it's getting too hot, or other infection rates. And you can also put some electrical stimulation on that, and like this also get a healing of the wound stimulated to become quicker. All of that, again, possible due to this vacuum deposition process. Now we're going to go fast, really fast, in transportation. Hyperloop. A train moving in a vacuum tube. So what we have now is actually a wagon which is put in a vacuum tube, and here you see a test track in the USA. And the state we're in now, the first humans actually traveled in this track. And the idea is that this goes really fast, and it goes all the way up to a speed of 1,000 kilometers an hour. And we can do that really energy efficient because we're in vacuum. The tube will be under vacuum. So if you are under vacuum, well, actually, the resistance by the air, so the friction with the air of the wagon, will go down and down, and thus there is no more friction with the air around it, so you don't lose energy. For instance, at atmospheric, if you travel at 800 kilometers an hour, there's 800 kilometers of air in front of you pushing. The resistance is 800 kilometers an hour. If you go all the way down to 1,000 of the atmosphere, you have only 25 kilometers an hour resistance. So it's like you use the energy for 25 kilometers an hour, but you can travel at 800. That's the idea of what they call Hyperloop. Transport under vacuum. A bit of theory. Mr. Boyle, a long time ago, discovered that pressure times volume is constant. So if you would have a volume enclosed in a piston with a kind of pressure on here, and you would lower the pressure, then the volume would become bigger automatically. This is, of course, important if you're working in a vacuum tube, which means what is a certain volume at atmospheric, if you go to a low pressure, well, the volume needs to become bigger. So this is something we need to take into account. And we actually use it by, if we connect two volumes, and one is under vacuum, the other is not, well, if we open it, the total volume will go down to half the pressure in between the two volumes. Pressure drop. What it means, well, in vacuum transport, people think it will be very energy efficient because there is not a lot of friction. But what people forget a lot of the time is that nothing is leak tight. Even very good materials, there is some air leaking into the vacuum. And this air needs to be removed, of course, because otherwise you don't maintain the vacuum. So if we would have 100 kilometers of tube, about 2 meters in diameter, for transporting a small wagon only, it's already 380,000 cubic meters of volume in there. You need to pump down to vacuum. That is already a lot. But you will have about 1,700 kilograms of air leaking in a very well sealed tube. So even if this tube is very high grade material, this is still the kind of air which comes in there. And to remove only this constant flow of air, well, you will need 1.8 million cubic meters an hour capacity of removing air if you want to work at 1 millibar. 1 millibar, you can go the quickest. However, at 1 millibar, you will need 500 vacuum pumps to keep the vacuum, just to keep the vacuum in this tube. And you would use 6 to 7 megawatt of energy just to keep the vacuum for the tube. As you can imagine, this kind of energy will actually make the total energy cost of transporting under vacuum way too high. So if you work at a higher pressure, the amount of vacuum pumps go down, and you can save energy. So one of the important things is, how well can I seal my tube? A lot of research is being done, because if the tube cannot be sealed very well, you need a lot of vacuum pumps and too much energy to make it economic. And also, it would be much more favorable to work at a higher pressure and lose a bit of speed, but that is not much. You will go from 1,200 perhaps to 1,100 kilometers an hour maximum speed, but also save a lot of energy like this. What people forget about, and what we just saw, is heat cannot be removed under vacuum. The vacuum is a very good heat isolator, thermal isolator. But if you transport people in a tube, and there will be an engine in the wagon in that tube, you will generate heat. So where can the heat go? Well, some people thought, put it in a vacuum tube, but that is not very easy, simply because the vacuum tube isolates, so you cannot remove it. So some people thought about the smart trick we saw with the bread. Evaporate water. If I evaporate water, I need heat. So let's put a tank with water on the wagon, and I evaporate the water, so my wagon keeps nice and cool. Well, the problem is the water will evaporate, and it will expand and generate a lot of volume, which you need to pump as well. Just to keep the wagons cool, it was estimated that the amount of water needed would actually increase the number of pumps needed to remove the air leak plus the water by a factor of 50. So all of a sudden, yes, your wagon is nice and cool, but you need 300 megawatts of energy to do it. So totally unpractical. So people now are thinking about having some cool pack on board of the wagon to do it. To remove the water, it also again depends on the pressure. We saw that in this phase diagram. Depending on the pressure, you need very cold temperatures, ice condensers, which eat up a lot of energy. Or if you are at higher pressure, you can use just cold water, and that is much cheaper, uses a lot less energy. Again, you see the feeling. Vacuum everywhere. The choice of vacuum pumps will influence the cost of the project energy-wise. And also the initial investment by the amount of pumps you need to do it. Finally, if you have a very long tube, you cannot simply pump on one side of the tube. If you pump on one side, yeah, you will have a pressure here which is adequate, but on the other side, because this tube will be a resistance, the other side of the tube will be at a much higher pressure. So in order to avoid that there is an uneven pressure, you need multiple locations for the pumps at every section. Let's say every 10 kilometers, you need a pumping station. Again, lower pressure choice, you need more pumping stations than with higher pressures. At higher pressure, the losses in the tube are not as big. Vacuum again. So initial pump downs, if you want to empty this volume to a low pressure, well, it takes a lot of time, the initial pump down. And again, the amount of pumps you need, the amount of time you need will really depend how much hardware you install. So if we would take the amount of pumps we use to keep the leak compensation, which I just showed you before, the tube would need 12 hours with 500 pumps to a very low pressure, 25 hours with 90 pumps. So you have less pumps. For the leak, it's okay. The pressure is higher. But if you want to pump down quicker to get the tube under vacuum much quicker, you will need to install some additional pumps as well. So that is additional investment. Even how you put a wagon into a tube makes a difference. If you would have at the end of the tube this vacuum airlock where you put the wagon in, well, you need to pump down the airlock, and all of that will add about 10% to the cost of energy for vacuum generation. If you would put it as an intermediate station, so it comes out of the tube in an open air and then goes to the next part of the tube, it could cost you about 40% extra energy. So what you can do is actually keep the wagon on the vacuum and just open the inside towards the loading dock and have wagons coming into this cigar tube. Again, vacuum technical solutions. Key advantage in conclusion will be, it should be a green transport, but the technology choices, especially the vacuum choices, will be extremely important to make it okay in energy. It is quite extreme if you make the wrong choices, so the wrong operation pressure, if your materials are not very leak tight, the amount of energy per kilometer per person is the same amount as you need to fly an F-16 fighter jet, for instance. If you do it right, it can be as low as a passenger traveling in a train, but at much higher speeds. What is worrying, all these companies like Hyperloop, and there are some others, well, they have a lot of dedicated staff working on this, engineers, where 60% is informatics engineers doing the design of the controlling and making all these nice simulations we see. I have not encountered any, and I've worked on 5 projects so far. None of these companies have a vacuum engineer, although vacuum is the key to make the projects work. So if somebody feels inspired, there is a job to take. Finally, I would like to close today with looking at the energy chapter. Energy for the future. What are we going to do about the energy? Coal, oil, somewhere we will burn it up, and on top of that, it's very bad for the environment, and we get global warming due to this. So energy is an important sector, and people have been thinking about energy and about the sun. The sun is doing what we call a fusion reaction. It actually fuses atoms together, and when you do that, they form a new atom and create a lot of energy. The sun as such, it will have a radiation power of what they call yottawatt. It's very high, 10 to the 24th power of watts. What we receive to the Earth, so only the power which radiates and touches the Earth, is already 10 to the 15th watts. And we actually consume only 10 to the 12th. So 2 options. Either we find a technology to create a small sun in a containment to generate this kind of energy ourselves. This is called nuclear fusion. And we will see as well, if we can capture this radiation of the sun, 10 to the power 15th, in an efficient way, there is more than enough radiation from the sun coming to the Earth to actually power all the requirements we have. Solar energy. Let's start with nuclear fusion. We get hydrogen species like deuterium and tritium. We fuse them together in special equipment. For this, you need very high temperatures and very high energies to maintain them. That is what causes the fusion. And as soon as these 2 molecules fuse together, they will produce a new molecule, helium, and some neutron. So no radioactivity, just neutron which you can absorb, but there is no permanent nuclear waste like you would have on a normal nuclear reactors as we know them now. So it's clean. It doesn't produce any waste, and it produces a lot of energy. Example, the sun. So people bought this, they built actually this special equipment, a thorax for it, and there is this hollow chamber where the temperatures will get very high in a very strong magnet field to compress all the reactive elements together. And the first demonstration of reaching the right temperatures was made in 1997 in the jet reactor. What people are doing now, we are now working on the next step, which is called ITER. And ITER is a much bigger fusion demonstrator reactor. And this one is actually designed that it can maintain the temperature, but also produce energy, because we want to produce energy. We don't want only to generate the higher heat to show that we can do it. We want to start the reaction, maintain the reaction, and extract energy. So this is what ITER is supposed to do. They are supposed to generate 50 megawatts, during 3,000 seconds. And as they achieve it, then the demonstration is done. And the multiple billions we invested, well, that's the end of it. We go to the next step and we build permanent production equipment. ITER is actually the biggest vacuum experiment in the world. The chamber itself is 8,500 cubic meters. So the thermal isolation chamber, the yellow one, 8,500 cubic meters. The green chamber, the torus, 1,330 cubic meters. Now you have to imagine an average apartment is perhaps 300 cubic meters in volume. So very, very big. And on top of that, they have cryogenic because they need to cool the area, and they will use very high power magnets, superconducting magnets, which needs to be kept super cold as well. All of this equipment requires a vacuum to make it operate. Finally, also in the torus, during the reaction, there will be vacuum. And I was fortunate enough to visit the site, which is still under construction. They are a bit delayed, I think about 5 years with respect to the initial planning. What you see here is this big cryogenic chamber, which goes around the reactor, which will go here in the middle. This is on the other side, you see the big doors, which are down here. And this is myself with one of my colleagues of Bush, France, which are standing on the other side of this wall where the big cranes are, which are lifting the heavy components to build the reactor outside of the building. And we need to be patient because the first time they actually will ignite this plasma and do the first measurements will be in 2025 only. So this is not our hope for saving the planet, because after this, when it starts to work, it will cost you another 30 years before you can go to commercial energy production using this technology. Which means we are going to focus, and we are focusing worldwide, on the other part of solar, which is the solar panels. You see more and more on the rooftop everywhere in the world. And actually solar panels generating power by solar, in 2050, they think it's 1/3 of the total energy consumption worldwide will be generated by solar panels and other advanced solar methods. So it's essential for getting the environment clean. To make a solar panel, so if you have this solar panel, you see there are these squares on top of that panel. Well, first you will get a material which is called silicon, which has to be sliced in these single cells you see on that solar panel. And these slices of silicon, well, they don't generate energy, so they need to be treated as well to get an active layer and an active material which transforms the solar energy in electricity. As soon as you have that active material, you need to compose it together in a bigger cell, which you can put on top of the roof. But if you would do that like this, it will very quickly not work anymore due to the influence of weather, the rain, the humidity, the wind, all of that. So you need to protect it, and it means they seal it into some other material so that it cannot be attacked by the weather. Very shortly, the solar materials start with the silicon. This is actually done by melting silicon in a very hot vacuum furnace. And in that vacuum furnace, they will start pulling with a small crystal first, this big rod. And this will be then the silicon material, which will be sliced. And you have the small cakes you need actually to build your solar panel. These slices, they will go in a vacuum coating equipment, because without any active material on the surface, you cannot generate electricity. So on the silicon, the blue side down here, you will need a couple of layers to make it active to generate energy. And that is done in these continuous streets where you have vacuum pumps here, a vacuum chamber, and here are the slices getting into the equipment. And this is where you use evaporation, for instance, and you need vacuum because otherwise these vapor, which need to go to the solar cell, well, they will hit too much air, like I explained before as well. Finally, once you protect it, you do that actually, you have a frame, so it's nice and solid, you can put it on the roof. A sheet of glass, but a sheet of glass will not seal, so there is a sheet of special plastic, a polymer, in between the solar panel, some more polymer, and some other plastic layer. And this stack is actually put in this chamber. The chamber, here you have the solar panel. On top, the orange part is a flexible membrane. And what you do now, you empty the air in top behind the membrane, and you empty the air around the solar panel. So everything down here gets under vacuum. You will heat it up, because if you heat it up, this special plastic film will start to glue the glass plate, everything together and seal it. And in order to really press it nicely, you use the force of vacuum. So this flexible membrane, if you put air in it and it's vacuum down here, it will be pulled against the solar panel and it will nicely, homogeneously press it together. Now, to conclude this quick tour to various examples of vacuum, this is where the planet should go. We should go to renewable energies. And as you can see, a lot of the energy will go to electricity. That is because the generation of electricity by solar panels is a very easy thing to do. So it also shows us that in the future, we will go away from any of those coal kind of energies. Cars will be electric, and we will go to batteries, but not only. Batteries and hydrogen. A lot of this energy will be used, the solar energy, to generate hydrogen, which will then be stored and be used later to generate the electricity. This is how we overcome the sun is not shining during the night. And hydrogen can store a lot of energy. So this is why, at the same time we are building batteries from lithium, people are also working on using hydrogen for electricity generation. So I hope I gave you a bit of a run through of most of the vacuum applications which we might encounter, but it's by far not all, because I can tell you everywhere you look at, vacuum is actually used. I'd like to thank you for your attention, and I would open now for questions if you would like to ask me something.
Thank you very much, Doctor, for this presentation. I'm pretty sure that every one of the participants watching this conference was really interested. In my part, personally, I didn't know many of the things that could be done with vacuum, especially that it had that of a great part in the creation of, well, the thing that will start the economy and our life back to normal, which are the vaccines, the COVID vaccines.
Absolutely.
No
vacuum, no vaccine. That's
yes,
easy.
Yes. Exactly.
So yeah.
So I think I have a question from my part before we go to the ones of the participants. What other applications we have seen that they have a lot in the current days in our current time, but what other applications could vacuum have on technologies that could help us in the future? We have seen the one of the fusion and the Hyperloop. Are there any other as important to our transportation energy?
Yes. As you might know, the electric cars, they use lithium-ion batteries. Huh?
Yes, yes.
You might have heard of lithium-ion batteries.
Mm-hmm.
Now, to manufacture the batteries, the material inside of the battery, even the electronic electrolytes, so the active materials, they are mixed under vacuum because they use lithium. And lithium, if it's in contact with air, it will burn.
Okay.
So they use vacuum to protect it. Then you need to protect the battery so it's leak tight because it will burn. You heard about these big accidents with telephones, which the battery got punctured and it starts
Yes,
to burn. Yeah.
yes.
So these batteries, they are sealed in a plastic bag. And to make sure they're really good sealed, they do actually what they call helium leak testing, another vacuum step. So they fill some helium in the battery, they put it in a vacuum chamber, and if there is a leak, the helium will go in the vacuum chamber and a detector will go off and know the battery is no good.
Okay.
One more example of what is happening at the moment worldwide, everybody wants to go to electric cars.
Yes, yes. That's the tendency right now.
Yes, absolutely. So, of course, medicine, it's everywhere. You will see it. Well, you must have heard cars can no longer be delivered because there is a big shortage of electronic circuitry, the so-called microprocessors.
Mm.
In such a typical manufacturing site where they make all these small millions of microprocessors we need everywhere, from our telephone to our car, all of the production steps. So that is 90% of the production steps. They are done under vacuum. Such a factory will have about 1,000 to 3,000 vacuum pumps for all the different processes. And without vacuum, there is no smartphone, for instance. There is no car anymore because all the cars are fully loaded with electronics. So this is why it's also very key to our future. And this is also why people are getting smarter and reinstall local production again. We have seen during COVID with the interruption, what it has done to our supply chains. And this is why at the moment, if you want a new car, you have to wait a long time, for instance. But I'm not that worried about cars. It's the same for medical equipment. If you want to have a respirator from Philips, they cannot deliver because there is no electronic circuit. So yes, and we are a small part of the effort to make it happen.
Yes, well, a big part, I would think. We have a question from Paula Rodriguez of Tec de Monterrey. What are the greatest challenges you have encountered working with vacuum?
Okay, so let's start with the most complicated challenge. So we, as a vacuum expert, we actually need to tell the customer exactly what he needs to do and what kind of pumping speed and everything he needs to do his process. And most of the people think, oh, this must be some high tech, like what I was mentioning, silicon chip manufacturing with all these very complicated equipments. The most complicated vacuum equipment is actually food packaging equipment. And this is because all the physical processes I tried to show you with these phase diagrams, everything is at the same time. First, the equipment is very complicated. So there are many pumping areas outside of the plastic bag, inside of the plastic bag, in front of the plastic bag, and all the vacuum levels need to be controlled there. And on top of that, they want to do it very quickly because you want to package one avocado set in a few seconds, because otherwise you cannot export a lot. Speed, second complication. And these foods are humid. So what happens if humidity gets at low pressure? It starts to cook and evaporate. So which means the vacuum needs to be pulled so quickly that only the surface of water will evaporate and freeze, sealing the rest of the food not to lose too much water. And this is for the consumer, otherwise it would not taste good, but it's especially for the meat manufacturing plants because water gone, there goes profit. Some of those, and now comes the tricky part you didn't know, they take the meat, they put it in a special stainless steel container with some salty water, they put it on the vacuum and then tumble it. It will absorb more water and then they package it. So you're buying water. That is the industrial way of making meat. So I really recommend go to the local butcher. There you get real quality meat. But yeah, food packaging is one of the most complicated challenges for vacuum experts.
Okay, I did not know that fact.
No. People think about high tech, but actually Hyperloop is pretty straightforward, but people like to forget about the vacuum part because vacuum they think is for free. And the only thing there you need to do is to learn that it's not for free, but the pumping principles are quite simple still.
Okay, we have another question from another student of Tec de Monterrey, Victor Máximo Samperio Avila. And the question is, renewable energies are the future of energy. Do you think that vacuum could be used or applied to them as a medium of energy transport or to make the process more efficient?
Yes, yeah. To give you an example where vacuum actually is critical for storing energy. And this is, for instance, you need a lot of energy very suddenly, and this is actually something which already exists. It's a sort of emergency power battery, but the kind which can deliver a huge amount of energy. And this is done by mechanical energy storage. So if you would take a very heavy wheel and you spin it very, very quickly, there is a lot of kinetic energy it's stored in there. Because when you hold the axis, well, yeah, the heavy weight will continue to turn, so you can recuperate the energy of the turning speed. But if you do this in a normal air chamber, the friction with the air will slow down the spinning wheel by air friction, so you cannot store the energy. So all of this is actually done in a big vacuum chamber at very deep pressure, no friction anymore, and they keep the wheel spinning at a very high speed. So when they need it, they can immediately attach the generators to the axis and recuperate a lot of energy. So yeah, a small example of one of the examples I know of where vacuum is actually making the storage process of energy efficient.
That's really quite interesting. And finally, we have another question of a student of Tec de Monterrey, Daniela Gomez. What do you think about the technology that was developed during this pandemic? What improvements do you think should be implemented?
Okay. Now, I think the key technology which was improved, I would say, during the pandemic, and I think it's an important finding for myself as well. Now I'm talking a bit from a person, is all the electronics. And this is also one of the reasons why we are installing more and more production capacity to generate more and more electronics. Because for me, the big revolution was video conferencing. Video conferencing has changed the life of many. Me as first, I used to travel 70% of my time international. So 70% of my working time. That will never happen again. It is actually now that I forced learned by COVID, you can work from home and you're much more efficient. I can meet you people, and I would prefer, of course, a personal meeting because that is still very important. But for many things, we can meet people now by the video. So I think the electronic revolution and the improvements, you must have noticed, Zoom, Teams, all of those programs got a lot more powerful, a lot more usable. That was a very, very big step for me. And I think we still see it. Intel in the USA is investing 20 billion US dollars. TSMC, one other big manufacturer, is investing over 100 billion US dollars for new factories. Samsung is doing the same because a lot of people are investing in this new form of working, a new form of working together. I think for me, for myself, for my personal feeling, this is one of the big revolutions. Of course, will be good for the planet, less people traveling, less pollution.
Yes, in that front, we are completely in the same opinion, Doctor. Well, life will change completely, both the school and work, with these new activities done online through video conferencing. And well, this Congress wouldn't be a reality without these capabilities of the different platforms.
Absolutely.
And with that note, we would like to thank you, Doctor, for giving some of your time to explain all of these important things. Very interesting, and well, I'm quite sure that we will have a lot of impact in the future with all these technologies. We're having them right now, and in the future, I'm quite sure it will be even a lot more with the vacuum technology.
Yes.
And we thank you very much. It was an honor to have you here, and
yeah. Thank you very much for having me. I enjoyed presenting. And if any questions come later, don't hesitate to contact me. I will try to answer them as quickly as I can.
Thank you very much, Doctor. I'm quite sure that some of the participants will have a lot of more questions. It was a lot of new...
It is a lot, yeah.
Yes, yes. I did not know many of the things you presented, and well, it was a mind opener of the possibilities of vacuum.
Again, feel free if you want to learn more about vacuum. I'm sure we can find a way to help you with that.
Perfect. Well, thank you very much, Doctor. We hope to
thank you as well.
Here again, maybe even in personal, face to face in the near future.
I would like that. Yes, yeah, of course. In the meantime, I wish you a lot of success by the rest of your conference, and I hope you have a good closing. And yes, perhaps in future we can meet in person and discuss more about the great world of vacuum.
I'm sure there's a lot more to discuss. Thank you very much, Doctor, and we hope to see you soon again.
Thank you. Bye, everybody.
Bye-bye.